And we're back. Let's hope that there's no noise anymore. Okay, so going back to the project. We've removed the interrupts from the SPI. So now the SPI is enabled, but it will not generate an interrupt. Let's try to compile and see. Let's see if I can remember the avr dude commands. Let's see. Let's open the project instead of just the file. Let's see, where can I find my main file? Right there. Okay, so let's rebuild. Is our hex file. SPIF0 doesn't exist, so let's change to SPIF, which is probably what it's set at. Okay, build successful. DVR dude exit, and let's see. USB ASP is my programmer. The part number is the 328PP, or was it M328PP? I can't remember. And then it's U. Command type is flash. We want to write and verify. The file name is 80 mega 328bb. Reset mod.hex. Let's see if he's gonna program it. Not recognized. Like that. Let's see, it looks like it's writing to the board. So let's open PuTTY on serial port. I'm gonna plug it back in. Let's remove the programmer for now. Let's check device manager. COM4. It doesn't look like it's sending anything. Okay, let's see. Let's try resetting it. There's a button right there. Yeah, it's not gonna do anything if the PlayStation isn't turned on, of course. So let's see, let's start PuTTY again. And let's turn the PlayStation back on. We are still reading our data, but we are still reading our command, but our data is still 0. Let's see, can I stop? So one thing I didn't take into account is the fact that the reading the bytes might not be in sync with the messages. As you can see, the commands start with 1, then 3, then 85, and then a few ones again. It should start with 3, then 85, and then a bunch of ones, which is still not correct data. So I'm guessing I'm going to try the transistor route. Let's see. Let's quit it for now. Let's turn off the PlayStation, turn off the microcontroller for now. I guess I'll just rewire this after I'm done with the transistors. Like that. Let's remove the level translator, level converter. Let's see if we can make this work. Let's grab our clock, which is this one. I'm just going to use a transistor as an open collector configuration so I can switch the input of the microcontroller high or low using a pull-up. Let's see what kind of transistor I'm using. It's a S9014. Emitter base collect. So I want my signal on the base, which is the middle pin. The emitter I want to be going to ground. Let's see if I can do something about that. Let's try plugging it like this. So this is what I'm going to try and make right now. Just basic building block. Just switching the output high or low depending on the input of the signal on the base of the transistor. So I should put the transistor with the emitter going to ground, the base be like that, the base goes here, the clock signal goes to the base, and the output, let's see, let's use a 1K pull-up. Come on. Okay, that's in. Let's take the oscilloscope to check if it's going to work. Let's grab the ground. Let's grab the pull-up. Let's see, blue should be ground, so I can put it here. And then I'd like to use the USB 5 volts, which is this one, which I'm going to plug right here. Let's plug in the programmer. Let's see, let me find another USB type B cable. I'll be right back. Okay, I found the second USB Type B cable because my programmer uses a Type B input, but the oscilloscope also uses a Type B USB input, which I need if I want to show you the screen of the oscilloscope. Let's see. Oh. Let's go to the desktop and webcam. So here's a little something I've been working on for the past 2 weeks. Hopefully it works, which it doesn't look like it's gonna do for some reason. There we go. Let's see, I can make it bigger, but I have to recompile. Takes a second though. Okay, let's see if I can measure just the voltage for now. Channel 1 is not being used right now. It's not measuring anything. Channel 2 is connected to the oscilloscope output, which I've now removed. Channel 1 should be measuring the 5 volts of the USB actually. Yeah, I haven't connected the... Let's see. Let's remove channel 2 for now. Looks like it's freaking out a bit. Let me try to run that again. There we go. So that should be the 5 volts of the USB. Let's see, I haven't attached the ground between the PlayStation and the USB, so let's do that too. Like so. And let's see if we can measure the input of the transistor, channel 2. like that. Let's see. That should be the clock. Let's enable channel 2. Let's put the channel 2 position back to a bit down, right there. And let's put both channels with the same vertical scale. Let's turn the PlayStation on. Let's see if we can turn back the scale, time scale. Okay, we are detecting something. Let's see, our trigger is on channel 1. And if you're wondering why I'm always putting my cursor onto the program I wrote for the oscilloscope, it's because whenever the program reads data from the oscilloscope, wait, let me show you if I can. Let's see. So whenever the PC is reading data from the oscilloscope has a little text right here. It's being remotely controlled. So if I try to press any of the buttons, nothing works. So the one way I found how to unlock the oscilloscope is by detecting if the mouse is on the in the window of the program I wrote, and if it is inside, then I'm sending a unlock command, which means that the program is not reading any data, so it's not updating anymore. So as you can see, I can change the time scale. Nothing happens on the PC. So let's see, let's put that to 0. No, no mat. Let's change the time scale. Put channel 2. And I'm triggering right now with a falling edge on channel 1. Let's see that better on the PC. Yeah, so this works without any issues. Let's see if we can do the same with all the other signals from the PlayStation, and then we can attach the Arduino to it. And as you can see also, because it's an open collector configuration, it's basically an inverter. So whenever the clock is high, the transistor is closed, which means the channel 1 is being pulled low, and whenever the input of the transistor is low, then the transistor is open, which means that the channel 1 is being pulled high by the 1K resistor I'm using. So let's remove the probes for now, so I can work on this. Let's change the view back to webcam. Let's turn off everything. like that. Okay, let's see, I need 4, I think 4. Let's see if I can arrange it a bit better. So I want one pin to ground, and I want the 2 others to be on the breadboard. So I'm just gonna put 1 pin to the back and 2 to the front, like that. Hopefully you can see. So I need clock command, data, slave select, and that's it. So that's 4. For transistors. So command is going here, data is going here. Put them a bit down so I have enough space for measuring later. Let's put our clock on 3rd position and the slave select. Ground is in the back. Okay, so now I just need pull-up resistors, which I'll just add in between. Just like that. So the resistors I'm using are 1K21. I didn't have 1Ks. Shouldn't really matter. I just want something not too big, not too low as a value. So that should be it. Let's see, let's try to grab a ground somewhere. Just like that. That's channel 1. Let's see channel 2. On the same ground, and I'm measuring command and data. Like that. Let's put the 5 volts back on through the programmer, and let's turn on the PlayStation. Let's see what happens. Let's increase the channel 1. No, let's decrease channel 2. Let's change the trigger, and I should be getting the output instead of the input. Like that. Let's trigger on channel 2, which is the 5 volt output I want. Let's see. So that's what I'm getting for the command. If we take a look at the clock, which is the green one, and then change our trigger to normal, change the time scale of channel to 500 millivolts, and there we get some signals. So let's zoom in on that. So that's the signal out of the PlayStation. Let's check the amplified signal, the inverted signal if you want. Let's put the time scale a bit down, the voltage scale, and let's do the same for the command. Like so, and then we see that the first command is a hex 1. Let's see, I haven't added cursors yet to the program, but if you look at the oscilloscope, you can see that the first clock pulse is reading a 0, which inverted is a 1, and the second clock is reading a 1, which is on the falling edge. You should read on the falling edge right here. So invert that and it's a 0, and then all the others are also high. Inverted, it's all zeros. So it should be x1, which is what we are expecting in our program, which is the select controller command by the PlayStation. Let's see if we can get the second command out of it. Looks like it's only sending one hex every time. Let me just check the TV and out of music. Why is that? Am I not playing any music right now? Okay. We have music again. So let me check the TV just to see if the controller is being recognized, which it is not. I wonder. Let's see, the controller is detected right now, but when I plug it in, it is not. So I wonder if we are loading if there's too much load on the lines. Let's see, we are on channel 1. Let's change our trigger. Yeah, that's way too much load. Let me look at the signal. So it's approximately 3 volts. Let's actually measure it on the real scope. We want voltage Vmax. So it's 3.5 volts Vmax, and when I plug it in, It's barely a volt. So let's see if we can add a resistor to that to see if it helps, or I might have to increase the 10k the 10k pull-up, the 1k pull-up resistor, sorry. Let's see. Yeah, that's the controller is still detected on the TV. Let's see if the output is still fine. Oh, what's that? Bad connection. There we go. That should probably be alright. Might have to increase it a little bit more. The voltage is being pulled a bit low. It's currently set to 2.88, 2.96 volts for channel 1, and channel 2 is approximately 5 volts. Let's actually measure the Vmax on channel 2, and it's displaying 5.2. So I might have to put a 2k resistor or something like that just to get the signal, just so it's not pulled too low enough. So let me take a moment so I can search for one. Okay, there we go. Okay, so I've got a few, just a few 2K2s. Just gonna put that instead of the 2K series resistor. There we go. Oh. I'm not getting anything on channel 2 right now, so maybe 2K2 is just, sorry, I pushed the camera, it's just a bit too much. Let's see, let me put back the 1K just to test. Yeah, so 2K2 might be just a bit too much. Maybe 1K5 should be good enough, because these one are 1K 200, 1.2K. So let's see, let's add a few extra resistors. Let's remove the channel for now, channel 2. And 2 more. Okay, control is still being detected, so that's really good. So let's see. These are our command. Let's measure our clock. Should be this one. Yeah, and as you can see, we are reading a lot of data right now, which we didn't have previously. So let's just check the inverted signals just to be sure everything is fine. Let's increase our time base. And let's trigger on channel 2, which is our clock. Like that. What you're seeing right now is just the first byte. From the command, shouldn't be an issue. Let's take a look at our data. The first byte should be all zeros. So let's see if we can move the data a bit. There, that's the second byte, which should be the device ID, and then it's the status of the buttons. Okay. let's see our slave select. Let's trigger on channel 1 right now, which is our slave select. And as you can see, we have some data in between the slave select. What I'm not sure about is why there's still a clock being generated after the serial select, the slave select is pulled low here. So this one shouldn't be here, and this is also a glitch. I'm not sure why it's there. I'm wondering if it's because of the circuitry I've added. Let's see. Let's measure clock. Let's measure like that, and let's see if removing the connection to the transistor changes anything, which it doesn't. Just checking if the control is still detected, and it is. Let's reboot the PlayStation. It's still the same, so I'm not sure what the PlayStation is trying to do right there. Let's see if I increase the data, if it's still doing the same. Yeah, it's still doing the same. Let's actually see if by plugging a memory card this goes away. It does not. Let's see. Let's try to read the memory card. Which is doing fine. Yeah, so I'm not sure what that small glitch right here, what's that supposed to be in this one. It shouldn't matter for the SPI, as the SPI is only active whenever the slave select goes low or high depending on your settings. So yeah, it might try to read something in here due to the slave select going low and activating the SPI. We'll try and deal with that later. But first, let's try to connect the. I guess it would help if I showed the oscilloscope. Let's So what I'm talking about is this here. I can increase the data by changing the controller from a normal digital mode to an analog mode. For those that know the PlayStation a bit, you might remember this controller. Whenever you press the middle button, the analog stick is disabled and the controller is basically like a digital one, and you press analog, the analog buttons are enabled and the analog stick is also enabled, so more data is being transmitted to the PlayStation, which is the increase in clock pulses you see on the screen. Like, this is the difference. The issue I was talking about is this added clock pulses right here. They are outside the slave select, selecting the device, which is a bit weird. It shouldn't send clock pulses whenever no device is being selected. Actually, it might be trying to communicate with the second controller. The PlayStation, I've mentioned this already before in a previous stream, but the PlayStation has let's take paint. Why is that so small? So the PlayStation has two controllers and two memory cards. Which, if you look at the input of the PlayStation right there, the port 1 is here with the memory card right on top, and the memory card for the second slot, and the control port for the second slot is right beneath that. So it's something like this. So like this, and then the communication between the PlayStation and the controllers and memory card is done with something that's mentioned as using transmit receive, a slave select pin. So let's see. So from the PlayStation, you're going to have one connection going to controller and memory 1, which is also going to go from control 2 and memory 2, and that's the transmit, or I call it the master rod serial in. Then you have the receive, which is shared between both controllers again. That is our Miso. or actually I'm gonna call it data, and this one is our command. Like so. Then there is a separate signal to enable or disable the controller and the memory card, which is your slave select. In this case it's slave select 1, and the controller 2 has another slave select, which is also going from the PlayStation, which is slave select 2. And then there's power, and ground, and also the clock, which is also shared between both both controllers. So we are only looking at the slave select for port 1 and memory card 1, the command, the clock, and the data. So what we are seeing here might be the PlayStation trying to communicate with port 2, and the channel 1 here, the yellow channel, is slave select 1, so we are not looking at slave select 2, which might be why why I thought the command was being sent when slave select 1 was high, but that's just because we are not seeing slave select 2, which I'm guessing is pulled low at this point. We can test it out by adding a controller to the PlayStation, so I can do that real quick. Okay, let's see, I have the controller right here. Let's see if adding the controller removes or adds some clock pulses. Just going to remove the memory card for now. I probably shouldn't put this here while it's on. Let's see what happens. There we go. So as you can see, our clock pulses increased and the glitch is gone. So it's looking for a controller on port 2, and because it doesn't find one, it just stops sending commands and it stopped the clock too. Why the slave select is going low after that, that's probably because of memory cards. not really sure. The memory card doesn't change anything, but that shouldn't be an issue. We can just detect a glitch and just bypass it if it's an issue. So let's remove the second controller and continue. Let's remove the memory card, we don't need it. Let's see if we can. Let's add all our resistors back in. I'm missing one. It's right there. Like so. Let's measure our output instead of the input, which should be inverted right now, like we saw before, but let's just double check. So we are measuring on the slave select. I'm going to change it to a rising edge. And so the channel 2, the blue channel, is our clock. Okay, it's time to connect the microcontroller onto the inverted signals. So let's see. Okay, I did not write the pins I need to connect. I pretty much know one SPI, but the second one I'm not sure. So let's see, the command should go to the master out slave input. Should be right there. The clock should go to the same clock as the programmer, which is this one. The slave select should be let's see, I'm not sure. This slave select. Let's go to the data sheet. And let's get the Arduino Nano pinouts configuration. So we are trying to connect the command to the SPI 0, which is right here, slave select 0, MOSI 0, MISO 0, but we are not using MISO, and clock should be PB5. So let's see, slave select should be on PB2, PB2 is pin 14. So slave select is 14. Or D10. D10 should be this one. And then the MOSI is on 15 or D11, which is this one. The clock should be on the other side on PB5 or D13, which it is. So now we have to connect the second SPI. And instead of using the command as MOSI, we are going to use the data. So we can read both the command and the data that's being transmitted. Data, and data should go to MOSI 1, should be PE3. PE3 is also ADC7, so ADC7 is A7. Which is right next to 5 volts. Should be right here. I think that's right. Let's see here. Then we also need the clock for the second SPI, and that one should be connected to PC1, which is ADC1. PC1 is A1. Let's see, A1 should be here. And then the slave select should be PE2. Which is ADC6, which is A6 on the nano board. So that should be connected. The only problem I see right now is that the slave select is a logic low input, which means that the inverted signal from due to the transistor is not going to work. It's not going to activate the SPI, so I should find another way to read the I'm not connecting that correctly actually. This should be going down there. I should be using the pull-up from the pull-up on the collector of the transistor. So let me remove the channels, oscilloscope channels. Like so. I'm gonna keep the slave select connected directly to the microcontroller. It should be okay to keep 2.8 volts. Let's see. Let's run the oscilloscope program again. So it's a bit above the 2 volts mark, and so the oscilloscope is saying that the voltage is 2.8 volts, but it looks like the controller is sending data through UART. You can see the transmit LED lighting up. So let's see. I'm gonna remove the power from the programmer and just connect the USB on the Arduino Nano board so I can read the data through PuTTY. Let's see. Let's open PuTTY. Let's check COM4. So we are reading inverted data because of the transistors inverting our signals. So let's invert it into the program. To do that, let's just XOR with 0xFF. That should invert the register. Okay, let's recompile. Let's flash again. There it is. Let's not do it whilst the PlayStation is on, just in case. It shouldn't send anything to the PlayStation though.
Too far up, just calm down. Get what you give and take what
Okay, that's done. Let's turn on the PlayStation. Let's power on the Arduino board. That's the data I need. So I'm looking for the command that selects the controller 1, which is x1, and I'm looking for the read command which is 42 hex, and looking at 30 right here, we can see that the command is reading 0, then 1, then 42, then a bunch of zeros, and then again 142. So I just need to synchronize the reading of the data. I wonder if I can re-enable the interrupts right now. Let's see. Let's try if we can enable the interrupts. So we need to add this PCI again. Remove the CLI. Re-enable the interrupt on SPI 0 and SPI 1. But CL interrupt was still programmed, so it's fine. We can remove this from the loop. We can add this back in. And we can add this back into the loop. And then something I added before is this timer interrupt. So let's see if I can show it again. Let's get our clock. And our slave select. Let's trigger on channel 2. So this glitch right here, I'm wondering if that's going to cause any issues. So I've programmed it. Let's see if I can show it a bit better. It's going to look at whenever the slave select is being pulled low. It's going to start the timer so that I can measure how long the slave select is being pulled low. So as you can see here, this time is measured, and if the slave select is high after let's say what's this, 5 microseconds, so let's say after 20 microseconds, if it's back high, then I just ignore the SPI. If it is still low, then I can continue reading my data. But let's try without. So let's recompile. Let's try to flash the thing again. I can probably remove the voltage, the power pin of the programmer, so I don't have to remove it every time. Let's see. Let's put some tape so I don't short it out. Like that, and now I should be able to plug the program back in without any issues, and I can program it. The PlayStation is on, so it's sending data, so let's turn it off. Okay, so that's done. Turn the PlayStation back on. Let's check buddy. Alright, I'm not inverting the data in the interrupt. My bad. Let's see. So this should be like that. And like this. PlayStation is up. Hello, Master 801. I'll show you. So I have a PlayStation right here, and I recently bought this thing, the PSIO, which is a device you plug into the back of your PlayStation if it has a parallel port. You can put in an SD card, and you can put your games in the SD card, and whenever the PlayStation boots up, it boots into the PSIO bootloader, where you can select your game. The only downside to this, or rather a feature that's missing, is that you cannot get back to the menu where you select your game once you have started that game. So you have to reset the PlayStation every time. The PlayStation has a reset button on top of the case, which is right there. That's the reset. But I'm a lazy person. I don't want to get up every time I want to change a game, so I'm trying to make a reset mod, which basically will reset the PlayStation whenever I'm pressing a certain button combination on my control. So what I've programmed right now is whenever you press Alt2, R2, start and select, the PlayStation should reset. So it's basically like pushing the button right here. That's something that the PSIO does not have, which is not, how can I say it? It's not an issue with the PSIO itself, it's just that the parallel port of the PlayStation does not have access to the information transmitted by the controller ports. So the PSIO cannot detect a button combination to reset the PlayStation. From what I understand how that thing works. So I'm trying to make my own. I've done a write-up about the first version of the reset mod. If you go onto my GitHub page, you can see I've explained a bit how this works. I've also included a video if you wanna look at it. It's like a minute long. It just shows you that by pressing a button combination of the control, the PlayStation will reset. Talks a bit about the installing the mod. Let's see, I have a picture. So here's how it was installed. So here you have your CD player, and here in the bottom right corner you have an Arduino Nano with a bunch of resistors, which is reading the information between the controller and the PlayStation. And I've decided to reprogram this because in the first version I'm using what's called polling. I'm continuously reading the inputs of the microcontroller to then decode the information and detect if a button combination has been pressed, and that's something I don't really like to do. I rather prefer use modules, interrupts. I find it's more elegant. It's a more elegant way to program, and it makes the overall code a bit more, a bit better, in my opinion. So let's see. I've inverted the SPI registers. I'm not sure if I already programmed it, but let's compile and program again. Okay, let's turn the PlayStation back on. Let's see, ready. One hex 42. That's exactly what I want to read. Let's see, how can I add the reset right now? I can probably just send the command again. So let's see. Let's print something to the UART. Like so. Let's rebuild. Turn on the PlayStation, program the microcontroller. Let's reopen PuTTY. And let's turn on the PlayStation. Let's try pressing the reset combination. There we go. Seems like it's reliable now. Oh, also something I forgot to mention, Master 801. The Arduino Nano uses a 16 MHz crystal oscillator, which means that if you look at the datasheet, the minimum voltage you have to use for a crystal oscillator which is higher than 8 MHz is 5 volts, and I was using it at 3.5. So having the voltage as low as it was, the microcontroller was being underpowered for the frequency at which each was running its instructions, which I was a bit concerned about the Arduino just glitching and resetting the PlayStation when it didn't receive any information. The voltage of the signals is 3.5 volts, and I didn't want to risk connecting 5 volts to the signals of the PlayStation, because I don't want to blow up the inputs and outputs of the PlayStation. So that's why I first used the 3.5 volt inside the PlayStation, which, by the way, I blew up the fuse. Let's see. Somewhere around here there's a fuse that I've replaced. Let's go to a bigger view. So right there, I don't know if you can see that. Right there, that's the 3.5 volts going to the controller, which I blew up by either connecting it to 5 volts or shorting it or doing something wrong with it. Yeah, so that's why I didn't want to use a step up. No, I'm using 5 volts, and I am connected to the PlayStation, but I'm using this small logic right here, which is just an open collector transistor. Let's see if I still have it open. I'm using this transistor, the S9014, in an open collector configuration. So just like this. So I have a pull up to the 5 volts, which is the output. Oh, sorry. Let's transition. So I'm using this S9014, and this is my circuitry. It's a 1K pull up to 5 volts. The base of the transistor has the signal from the PlayStation attached to it, and the output here is going to the microcontroller. There is one signal I'm not going through a transistor, which is the slave select, of the PlayStation, because the transistor basically inverts the signal going to the base. So whenever the input to the base is high, the output is low. And the slave select should be a logic low signal. If you look at the datasheet of the 80 mega which is used on the Arduino Nano board, the slave select has a line on top, which means that it's going to activate the SPI modules when the input goes low. And if I invert the slave select from the PlayStation, then I'm enabling the SPI whenever there's no communication. So right now I'm just using a direct connection to the microcontroller. It's not that great. I don't really like that, but I know my code. I know that I'm not going to set the I know that I'm not going to set PE2 to a 5 volt output, so I'm not going to set it high, and thus possibly shorting the PlayStation output to 5 volts. And that's pretty much it. Yeah, I didn't think I would finish so quickly actually. Looking at the data we were getting before, let's see. So if you look at the commands and the data that we were getting, so we want 0x, 1 0 1 42 and then 0 and a bunch of zeros, and we were getting 0 3 8 4 and then I think 0.01. Something like that. I wonder if I just didn't set the SPI correctly, because when I inverted the clock, I didn't have to change the read on rising edge or falling edge, which is something you have to set. So I guess I was reading on the wrong edge of the clock. But yeah, anyways, I'm glad it's working now. Let's see if I can make it a bit more reliable. So if you look at the information right here, I'm receiving 9 bytes, which for a digital controller is not needed. Let's see. So a simple, in case you didn't know, this is the website from Nocash, which has a ton of information about the PlayStation. So for a digital controller, the data transfer is only 5 bytes. So the PlayStation sends a 1 hex to the controller, which responds with a high impedance. Then the PlayStation sends a 42 hex, which is the command to read the state of the switches. The controller responds with his ID in 2 bytes, ID low, ID high, which in our code is defined right here. So for a digital controller, we are expecting a 5A41. For both analog controls, we are expecting a 5A73 or 5A53, and for the light gun control, we are expecting a 5A63. And then we read two bytes, which are the status of the switches. And here they are defined. So you start with bit 0 is select, then you have the L3, R3, the start button, up, right, down, left, L2, R2, L1, R1, triangle, the circle, the X and the square. Why did I choose an Arduino over an FPGA? Just cheaper overall, or is it just not needed? An FPGA is not needed for this. FPGAs are really expensive just for this. And the Arduino is just the size of the Arduino Nano was just right to put it right where I've put it before. Like you can see in the images here. So yeah, an FPGA is overkill. Also, there aren't a lot of FPGAs which are 5-volt tolerant. Most FPGAs are like 3 volts, 1.8 volts. They're also working at higher frequencies, like you can go to hundreds of megahertz, sorry. which again, it's possible to read the information of the PlayStation with the FPGA, but it's not something I need. It's just going to make the cost of the mod way higher than it actually needs to be. So continuing the explanation about the controller data, the analog controller will send 4 extra bytes, which are 16-bit ADC values, 2 16-bit ADC values, which are the analog controller position, so the right analog X and Y position and the left analog X and Y position. If the controller connected to the PlayStation is the light gun, then we are only looking at, let's see, not sure if it's put it in here. So the same 2 bytes for the switches are read if the light gun is connected to the controller, but only bit 3 is used for the button A, bit 13 for the trigger, and 14 for the button B. If you don't know what that gun looks like, I can show you. Let's see. So this is my mic cable. So this is the light gun. It has a trigger button, a B button on this side, and an A button on this side. Pretty cool controller, if you ask me. So the special thing about the light gun is that it reads the screen. It sends a 16 bit value, which is a 8 megahertz clock since the horizontal sync, and then it sends that's the X position of where you are aiming on the screen, and then it's sending another 16 bits value, which is the Y position, and that's just a counter that will count every V-sync. It's pretty cool way how they did that. So their X position, the screen X position is divided by an 8 megahertz clock, so the precision is pretty cool, pretty nice. the range is pretty high. Yeah, that's pretty much it about the controllers. Let's see, I guess I should try to put the Arduino back inside the PlayStation. So let's see. I'm using pin D6 to reset the PlayStation, which is D6 on the Arduino. Let's see if I'm initializing the pin correctly. I'm setting all inputs to all I/O from port D to inputs without pull-ups, and then in the check switch combo if statement, I'm setting the direction register of port D so that the D6 input output is set to an output, and then I should set port D6, which actually is reset, and this should be port. So I'm setting the output high. I should set it low actually. So yeah, the port is already set to 0, so I want to pull it low so that the reset line goes low. And so I just have to change the direction register of port D like this. And then I'm just going to wait like 100 milliseconds between setting the output low and putting back into high impedance mode, so that the PlayStation has enough time to reset, basically. After resetting the PlayStation, I'm going to have a reboot delay, which is going to be 30 seconds. This is a delay that should be put right here too. Let's see, right there, because I don't want the user or myself to reset the PlayStation I don't want anyone to reset the PlayStation while the PlayStation is booting up. Yeah, so I'm adding a delay just for that. And that should be pretty much it for the program. I'm gonna keep the UART for now. Let's program the controller again. And connect the reset to the PlayStation. So let's see, I want PD6, which is D6 on the Arduino. Let's change the view to the webcam. For now, I'm just going to connect it to the power board, which is right, let me get something to point with, which is right here. This jumper here is the reset, but you shouldn't use this one. I just don't want to remove and solder on the backside of the PlayStation motherboards just yet. The parallel port right here has on the backside has, I think, pin 2 should be the reset line for the PlayStation, so you should use that one instead of the one on the power board, just because it's safer and it's just better. Okay, let's see if I can solder on a small wire onto there. Guess I'll just choose a small dipole wire. I'm gonna add some solder though. Let's add a bit of solder to the wire too. Like that. That should do it. Then let's connect PD6 to the Arduino. I'm just using this as a link between the reset and the Arduino. Let's see if I can show the PlayStation right now. So that's the screen. As you can see, if I push the directions, the cursor moves right here. So that means it's still detected. So now if I press let me open PuTTY just to see the data before. Let's see, just in case I didn't connect the Arduino correctly. It's still going to show PlayStation reset in the command, in the PuTTY. So let's see, L2, R2, reset start, and that's the PlayStation resetting. Let's see if it's going to and it is. So that's the mod. Let's put the camera back. So that seems like it's working alright. I'm gonna take a quick break. Do you plan on making it more miniature than it already is? I might. It's always possible to make it smaller. Like right now, the Arduino board is just for convenience. Yeah, I could use an ARM chip. Those are usually 3 volts. I shouldn't have any issues with the PlayStation voltage. Yeah, or I might just try to find another 8-bit microcontroller which can run at 60 megahertz like the one I have right now, but then at 3 volts instead of 5. And yeah, a custom PCBA would be cool to have. Let's try and see if we can find the ARM chip. Which is 3 volts and like 16 megahertz or more. I guess the oscilloscope we don't need it anymore, so let's just turn it off. And let's show the desktop. It's the propose. Probably something 8-bit would be easier to program. Yeah, I get what you mean. But then again, I've already tried to search for an 8-bit microcontroller which is 3 volts and 20 megahertz or 16 megahertz, which has 2 dedicated SPI modules, and I didn't find one in the Atmel. We put in the but I did find the 80 mega 328 PB, which is the normally when you buy an Arduino Nano you get the 80 mega 328P, not the PB version, and the 328P only has 1 SPI, and I wanted to use 2, so I bought the 80 mega 328 PB, and I've replaced the 80 mega on the Arduino with this one. But yeah, other than this one I haven't found one yet. So let's take a look at the one STM is proposing. Yeah, see there, the microcontroller only has one SPI. You know what? Really? Who the fuck designed this website? Anyways, so as you can see, the SPI, most of the STM8 only have one SPI, so that's not what I'm looking for. What's the voltage? These are all 5 volts, from 3 to 5 volts. Let's see. Did say anything about 60 megahertz right there? 60 megahertz. They don't say the voltage. But yeah, Steam is already crossed. Let's go to the microchip website. Let's see what they have. I can never find their stupid search engine microchip website. The selection tool. Let's see. I want 8-bit AVR and I want 8-bit PIC. SPI, I want everything that's bigger than 2. So let's see. Let's check the first one here. To see if it's suitable for the project. Let's check the data sheet. Operating speed 32 megahertz, so that's already nice. Operating voltage range, so the LF version, the low voltage version, goes from 1.8 to 3.6, and the other goes from 2.3 to 5.5. It has SPI, but we should check how many SPI it has. Crystal up to 20 megahertz. Really? Which one do we have? The 18325, 18325. It has two. Looks like it has two SPIs. Program flash is 14K. How much is ours? It's 1K approximately. So there's more than enough space in there. And let's see. So SEK1, let's select one. Let's select two. I'm guessing they're using SDA and SDO and SDI for Mizo and Mozy, so that should work, I think. Let's see if they say anything about the minimum voltage needed for a given oscillator. Let's see if I can find it in the 80 mega. I can have a reference. Not sure where I found that. Probably somewhere here in the electrical characteristics. Yeah, right here. Maximum frequency versus input voltage. So at 20 megahertz we need to have at least 4.5 volts for the 80 mega 328E and 3B. Let's see if we can find the same thing somewhere in here. Oh, nice. So we can use both the F version and the LF version. Which can use 16 megahertz at 2.5 volts minimum, and also between 2.5 and 5.5. That's nice. I'm gonna keep that in mind. I'm gonna write that somewhere. We might do something with this. Let's see how we can get it. So Winnipeg or SOIC. Yeah, probably SOIC would be nice. So let's see, I'm gonna write that down. A peak 16F 1A325. Which can use 3.5 volts at between 60 megahertz and 30 and 20. The architecture between the PIC and the AVR is a bit different. And so on the PIC, I think one instruction is executed every 4 clock cycles. Let's see, it's not saying anything about MIPS. If we take a look at the 80 mega, up to 20 MIPS through throughput at 20 megahertz. So it's basically one instruction per clock cycle. Let's see if I can find the same thing in here. No, it doesn't look like it says anything about MIPS. Let's check out the SPI modules in this. Would be has SP. So it does pi and it does I squared C. FOC divided by 4 is the minimum frequency you can have, which at 60 megahertz it's 4 megahertz, and the SPI of the PlayStation sends its data at 250 kilohertz. So that should be enough. Yeah, we might do something with this one. Or we could go with the 80 mega 48 PB, which is again the same version as the 3 to 8 PB I'm using, but the smaller package. Let's see. No, this one doesn't have two SPI modules. Only has one. You can choose this one. No, because it's 48 PB, 88 PB, and 168 PB. So we can choose either of those. I guess we can try the 18325 on microchip instead of an AVR. It's also fairly small, like 14 pins. Yeah, that can be a nice upgrade to the AVR we are using currently. I'll see if I can buy some for next stream. Let's see, what can we do? We could install this mod in the PlayStation, but then I'll have to remove it if I use the big one, or we can wait until next stream if I can get them quickly enough, and we can try programming the PIC 16F 18325 and then install the mod inside. Yeah, I think I'll go with the second option. I'm gonna end the stream now. We've been streaming for like 2 hours 47 minutes. I'm gonna buy some 16F 18325. Hopefully they'll get here before next Saturday or Sunday. I can stream next Wednesday because I'm working, and then hopefully we can play around with some microchip microcontrollers instead of AVR. Yeah. See ya.